All right, hello everyone.
Hello.
Lots of Zoom lecturing today, I guess. This is my second class. There's a number theory seminar at 4:30. Anyway, all right. So, any questions before I get into it? The format seems pretty straightforward. I think we're just trying to make our way through the very basics, not to say trivial stuff about group homology and group cohomology. And then I think soon enough we'll make our way to Galois cohomology, and it proceeds like this for some time. Okay, so if not, let me share the screen. Yeah. Um, I don't know. On the one, I kind of wish we were going faster relative to where we are in the book, and what it would be nice to cover. On the other hand, I don't think we've just been, walking in the park or whatever. We've been doing stuff. So anyway, what are we talking about? We're talking. Last time we defined if you have a subgroup of a group. You can certainly restrict a G module to get an H module, either directly through the definition of actions or through just by looking at it in terms of modules over group rings. And then it's in general a good question to ask, is there something that goes in the other way, right? So this diagram is kind of too simple to indicate the actual story that's happening here. So we asked the question, um, if I have an H module, can I is there some induced G module? And the answer is yes, but it's a bit of an embarrassment of riches situation. In general, there are two ways to do this, okay? Um, and so the one case, the more sort of homological way to go. So by definition, the induction of a ZH module from H up to G is that you take it and you tensor it over ZH with ZG. Okay, so we discussed this, and then just from the theory of tensor products over modules of over tensor products of bimodules over non-commutative rings, then this naturally has the structure of a left ZG module, which is fine. And then the co-induction, well, you literally, instead of tensoring with ZG, you Hom with ZG on the same side. So the co-induction is the Hom in the category of ZH modules from ZG into M. So that's just the H invariant group homomorphisms from ZG into M. Here it's not completely standard what G action to put on this, and this is the G action. So we put G acts on the function by when you evaluate it at X, you kind of right translate X by G, and then you apply. Okay. Let's see. Again, if you were hoping to see the G on the left, check that just doesn't work to give an action. Okay, so that's one part of that, and then we had some discussion about that. Okay, and where were we? So yeah, so we proved, frankly, just some pretty technical, not so important things about induction and co-induction last time, just really kind of, in terms of subtleties about G module structures and such things. Right, and then let's see. Yes, this lecture, I kind of did everything but advanced the theory of induction and co-induction, which is what I want to do in this lecture. So I reminded you, um, even if you haven't seen it before, that it just in classical representation theory. So what does classical representation theory mean? The most classical thing you could do is have a representation of a finite group on a finite dimensional complex vector space, right? And in that situation, this idea of studying representations of a finite group, probably a non-commutative group, the classical representation theory of finite commutative groups is very easy. And so you can study the representation theory of a finite non-commutative group in particular in terms of induced induction from cyclic subgroups in this theorem of Arden, and in terms of products of cyclic subgroups and p groups in this theorem of Bauer. Okay. And so, yeah, so throughout representation theory and even the most kind of lowbrow connections between representation theory and number theory, you're going to see induced representations all over the place. I mean, one question, I think I'm not even going to answer this. I could have answered this question at any time, but as a simple answer, I think I'm not even going to answer the question in this lecture, so you're going to have to wait for it. Where's the co-induction, in the theory of finite groups, right? So I defined these two things. You can do induction and you can do co-induction. I'm telling kind of induction is sort of like a homological thing, and induction is sort of like a cohomological thing. We'll see much more of that in a second. And then I told you that induction was the most important thing in the representation theory of finite groups. Why is co-induction not important in the representation theory of finite groups? So I mean, maybe I'll just have it in certain special cases, induction and co-induction become the same thing. So that's the spoiler. Not in general, but there's a very simple situation. There's a precise result under which induction and co-induction become the same thing. However, they're not always the same thing. And in general, they behave differently. So I think you should study the way induction behaves in general and the way co-induction behaves in general, and observe that they're the homological and cohomological sort of siblings of each other, and then appreciate that in a certain case they collapse to the same thing. Okay. All right, so this I think begins this lecture. So only in the overtime of the last lecture, which by the way, I think I forgot to post it for a while, so that was just a mistake. I apologize. I did post it this morning. So here's the result that I want to spend most of the lecture proving today. Okay, so this most people that I know call this Shapiro's lemma. Apparently, it is due to Ekman, Fadeev, and Shapiro. And having said that, I will usually call it Shapiro's lemma. Okay, and so this is definitely explaining why we care about these things. So quite general, I have any subgroup of any group, and then n is an H module. And then for all non-negative integers n, we have, for most of the rest of this lecture, I'm going to write equality if I mean a natural isomorphism. Okay, so these really are natural isomorphisms. Okay, isomorphisms of functors. Okay, from, maybe it's better to write it on the other side. So the homology groups of the H module n are also the cohomology groups of a certain G module, namely the induction of n from H to G. Okay, so you got to appreciate that. And then similarly, the cohomology groups of an arbitrary H module n are also the cohomology groups of a certain G module, namely the co-induction of n from H to G. Okay, so this is a very, very important close relationship between the homology of a group and the homology of its subgroups, and the cohomology of a group and the cohomology of its subgroups. Okay, so in particular, yeah, so the homology and cohomology of subgroups is sort of literally a special case of homology and cohomology of the group itself. Okay, so that sounds like it's got to be important. And then before I prove it, I think the next thing that happens is I spend a couple of pages explaining why this is important. And in fact, believe it or not, the most important special case of this is actually when H is trivial. Okay, so yeah, maybe I should remind you. So what does it mean to be induced or co-induced? So that's the special case when the group is trivial. So if I just start with a ZH module when H is the trivial group, in other words, I just start with a Z module, then I can induce from the trivial group up to G. Okay, so that's just taking my abelian group and tensoring it from Z to CG. I said abelian group again, darn. And then the co-induction of a commutative group or a Z module is the analogous thing, the cohomological thing. I take the HOM just as abelian groups, damn, the HOM as Z modules from ZG into A, okay? And so one calls a ZG module induced if it's isomorphic to one of these guys, and one calls a ZG module co-induced if it's isomorphic to one of these guys. And now, of course, like, why do we care? And now as a consequence of Shapiro's lemma, we see why we care. So the induced G modules are going to be acyclic for group homology. So what? Okay, this is some homological algebra. If you have some left exact functor that you're taking the right derived functors of, or I guess I should have said the other way around first. First, we have a right exact functor, the co-invariants that we're taking the, sorry, I had it right the first time. The co-invariants are let me stop. The co-invariants are no. Sorry. The invariants are right exact, and we take the left derived functor, so that's here. The co-invariants are left exact, and we take the right derived functors, I think. Sorry.
I think you said that backwards.
Yeah, let me stop,
Okay.
just take a breath. So I think I'm also confused among other, I mean, it's been a long whatever, but I'm also confused by the fact that I switched the order from the way I first started talking about these things. So if I first start talking about, so we defined the co-invariants first, right? And so the co-invariants were right exact, they were not exact in general. Therefore, you have left derived functors, which give you a cohomological delta functor. Anyway, in such a situation, or in a situation where you have a left exact functor and you take the right derived functors, either way, you say that, so these are functors, and you say the functor is, you say that an object in the category is acyclic for that either left exact functor or right exact functor if all the higher homology or cohomology groups, all the homology groups with n greater than or equal to 1 are 0. Okay, so that's the definition of what it means to be acyclic for a left or right exact functor, sort of equivalently for the associated homological / cohomological delta functor. Okay, and so we see therefore, I mean, it must be.
What about the opposite direction? If it's, I guess, acyclic, is it induced or?
Sorry, so let me just say, so if it's induced, then you can see from this, then here induced means, we take H to be the trivial group, right? And so certainly the higher homology of the trivial group and the higher cohomology of the trivial group is trivial, right? Because both invariants and co-invariants are fully exact when the group is trivial, okay? So if it's an induced G module, then it's acyclic for group homology, according to this. And if it's co-induced, then it's acyclic for group cohomology.
Yes, what about the other way around? What if it's acyclic? Can you say that it's induced or co-induced?
Oh, that's a good question. So we'll see. In fact, no. In fact, we'll see in just a second. I'm gonna introduce a slightly more general thing, which is still acyclic. And I guess I don't have a counterexample in mind, but why would we introduce this slightly more general thing if it weren't actually more general? So probably not. But very good question. Okay, so I didn't understand your question. Yeah, and again, the proof is immediate, as I just told you. Okay, so now a little preliminary result, which is going to help us for the thing I want to say next. That's how preliminary results work. So every G module whatsoever is canonically surjected onto by an induced G module, and every G module whatsoever is canonically injected into, every G module canonically injects into a co-induced module. And so if I have a G module and the least imaginative way that I could make an induced G module out of it is just to sort of is just to sort of forget the G module structure and just think of it as a Z module. And by the M-circ, I think I'm just emphasizing here. So by M-circ, technically I mean make the action trivial. And so that's just so as not to confuse you, right? So I shouldn't be inducing a G module. I should only be inducing a Z module. So I'm putting the circs here so that you understand that I'm forgetting about the G module structure. Okay. So right, and so these are the proofs are not so hard. So right, so what is the map in both cases? So again, what are these things? This induction really is just this tensor product, and you look at this and you're like, I think I see a map, right? How about I take G tensor M to G times M, right? And then take finite sums to finite sums. That's definitely a Z module map. The only thing that you have to do is check that it's a G module map. Okay, let's check that it's a G module map. Some other group element H, if we hit it this way, well, P multiplies them and then we multiply by H, so that gives us HGM, but that's the same, of course, as saying P of, we can unmultiply them and get HG tensor M. And now's the part where we have to remember that I put the circ here. So now if I'm wondering what the G module structure is on the tensor product, it's not the diagonal G action, it's the regular G action on the group ring, literally, and it's the trivial action on the second factor. And so indeed, HG tensor M, although it looks rather asymmetric, is H applied to G tensor M. Okay, that's it, we're done on that one. And then the other one is maybe a little bit more interesting. So again, if you just sat quietly, I'm sure you'd figure out what you want the map to be. So now I want, given, let's see. So given an element of M, I want a Z map from ZG into M, or equivalently, I just want a map of sets from G into M. And so, okay, if you think about that, what is my map going to be? My map should be, take your group element G and multiply it by your fixed element X. Okay, so that's what the map is. X in M is being sent to a certain map from G into M. Where does that map send G? It sends it to G times X. Okay, and so this is this is no problem to see that this is a map of commutative groups. So to see that it's an injection, I just have to check what goes to 0. So if iota of X is equal to 0, well, then everything is equal to 0, but iota X evaluated at the identity element, which I've now started calling 1, the identity element in the group, well, it maps the identity element to X. So it's only 0 if X is equal to 0, so it's certainly injective. And then again, I should check that it's a G map and no big deal. Okay, so if I multiply it by H, okay, then again, what is my G module structure here? My G module structure is I multiply my input on the right, okay? And so that's what I'm doing, as I just recalled. Okay, no problem then. So iota X of GH is take GH and multiply it by X. And then if you think about that, that's iota sub H of X applied to G, because again, take G and multiply by whatever the subscript is, right? And so then what is that? That is, what is that check? That check that as functions, then that check that H applied to iota of X was iota of HX, and that's the G map, G homomorphism condition that we want. Okay, so no big deal. But this is a very useful result. Yeah, so now comes the definition that is going to address Menzel's question. So first of all, a very easy fact. This is general nonsense, if anything, as group homology and group cohomology commutes with finite direct sums. Just because they're additive functors or something. I mean, that's not. Take whatever definition of group homology or group cohomology that you're being given, and before you wake up, you'll prove that this is true. It's not that. Okay, and so now comes a definition. So the definition looks a little bit strange at first, maybe, and we have to try to understand the significance. So a G module is said to be weakly projective. Equivalent, maybe slightly more common is relatively projective. I like weakly. Weakly sounds better to me than relatively, so I'm going to go with that. Hopefully, projective modules should be weakly projective, right? That should be the next result. If it's a direct summand of an induced module, okay? And it will be weakly injective if it's a direct summand of a co-induced module. I mean, yeah. So there's sort of 2 points here. Yeah, maybe I should. Yeah, it is true. I'll go in order. It is true that projective implies weakly projective and injective implies weakly injective. So let's go through the proof of that. So suppose you're projective. Well, by what I just proved, like any module, you can write it, you can surject from an induced module onto it. But hooray, I'm projective. So when I have a surjection, that gives me a short exact sequence. In general, a short exact sequence doesn't split, but it definitely splits if it terminates at a projective object. That's the definition of a projective object. And so right away, we see that every projective module, by virtue of being surjected onto by an induced module, so therefore this induced module is the direct sum of P and the kernel. And so therefore the projective module is a direct summand of an induced module, which by definition makes it weakly projective. Guess what? Reverse all the arrows and you will prove that injective G modules are weakly injective. Okay. So, but okay, here's the point that answers Menzelos's question. Right, so by this same easy fact, if you take two modules, G modules M and N, and their direct sum is acyclic for group cohomology, well, look, that means that for all n greater than 0, this guy has to be 0, but this guy is the direct sum of two other things, so both of those things have to be 0. So certainly if the direct sum is acyclic, then so are M and N, and therefore it follows that weakly projective modules are acyclic for group homology and weakly injective modules are acyclic for group cohomology. And so yeah, so I do not think that, I gather anyway, I haven't really thought about it carefully for a while, but I do not think that it is true that every weakly projective module is induced and every weakly injective module is co-induced. Of course, now you can still ask me about the converse. I can think about it. Yeah, I don't know that I have a. Yeah, it's a good question. These are kind of these. I think it's a sort of a cheesy answer, but sort of in practice, these are the acyclic objects that we really like to work with anyway. And so it's sort of, if they're we found a class of acyclic objects that are so easy to work with and so ubiquitous. And so if there are more acyclic objects, I'd like to know too, but we don't really need it. Okay, so let me write down. So there's a very important consequence of this, which goes by the name dimension shifting. So let me do it in the induced case first. Let's see, right? So weakly projective modules are acyclic for group homology. In particular, induced modules are acyclic for group cohomology. And then again, the fact that once again, every module whatsoever is canonically a quotient of an induced module. When you go and take homology, that becomes very useful. Right? We're going to have a long exact homology sequence, which because it's homology, I'm a little slightly burned from preparing too many lectures, but I'm still pretty sure the long exact homology sequence will go from right to left. And so I haven't written it down, but if you just write it down, then as soon as n is large enough so that this thing in the middle is always going to be 0, then you're going to be getting your boundary maps between the nth homology of the kernel, right? There's a boundary map from Hn of Gk into Hn plus 1 of Gm. That's kind of the boundary maps are the most interesting maps in this long exact sequence. And so I believe for all n greater than 0, the nth homology of the kernel is equal to the n plus first homology of the module itself. And then you can even say something, I think it's true that if you take n equals 0 here, then, oh, something must be a mistake. They can't both be m. Which one do I mean? I think this should be a k. Wait, is that right? Sorry, let me think. H1 injects into H0? Yes. All right. Doing homology and cohomology at the same time can be slightly confusing because you have to reverse all the arrows in your head. Anyway, so this is giving you this just turns out to be super useful for a lot of things. And so why is this useful? It kind of manifestly is useful because you're expressing higher homology groups of your module in terms of lower homology groups of a different module. So, in principle, there's, an H3 of something is going to be an H2 of something else. Okay, and so that really sounds like it could be useful, and it is. So that's the homological dimension shifting. And then there's of course there's a corresponding cohomological version. So every module gets canonically embedded into a co-induced module, and you do the same thing because the co-induced module is acyclic for group cohomology. Then at a certain point, so I believe this is true now. Now the long exact sequence is going from left to right, and you have a co-boundary map from the nth cohomology of C into the n plus first cohomology of M, and yeah, so for all, as long as n is at least 1, the two guys, between those two maps are acyclic modules, and so yeah, so you're going to get canonical isomorphisms there. And then if I did it right this time you can't say that you have an isomorphism for the smallest possible value of n here, but because what's the point? The kernel of this map is the H0 of the co-induced module, and so I didn't say that H0 was 0. That's kind of ridiculous. It might not be an injection, but the co-kernel is the H1 of this acyclic module, and so that's 0. Okay, so again, with any luck, we'll see this coming up in practice, but this is a very, very important technique for working with group homology and group cohomology. So using this idea of dimension shifting, you can often reduce questions about higher homology groups or cohomology groups down to questions about lower, despite the fact that there was a little bit of trouble at 0, but nevertheless, in certain cases, you can kind of successfully dimension shift all the way down to dimension 0. Okay, so any questions about that? That's kind of the end of the first half of this lecture, I suppose. So that was my first lecture on induction and co-induction. Okay. What did I want to say? Another thing, I guess I was expecting it to come up in context. Why do we care about acyclic objects? There's this theorem in homological algebra. It's not a tough theorem. It's in my notes on homological algebra. I'm sure it's in the appendix of Harari as well. One reason to care about acyclic objects is because a priori, if you have a right exact functor and you're taking its left-derived functors, a priori the recipe says you should take a projective resolution, right? And the idea is that like projective objects are universally acyclic for any right exact functor. If you look at the left-derived functors of that functor, then all the higher left-derived functors will be 0 on projective objects. So projective objects are universally acyclic for homological delta functors, like let's say, or for oh man, it's been a long day. Right exact, left exact. Oh dear. Man. Sorry, which is it again? So if we're doing, if we're doing homological delta functors, yeah, so now I'm kind of turned around. If we're doing homological delta functors, then right. Yeah. So if it's left exact, yeah, I'm sorry. Okay. Right. Yeah. So right. So right, I said it right. So for right this time, if my functor is right exact, then I take left derived functors and I get a homological delta functor. Okay. And so projective objects are universally acyclic for homological delta functors. However, for your particular homological delta functor, there may be non-projective objects which are acyclic. We just found some. Okay. Or for instance, if not unrelated at all, if your functor is tensor, right? Then flat modules are acyclic for the tensor product, which is is closely related, but is more general than a projective module. Okay, and so the theorem I'm getting at here is that if you're trying to compute the derived functors of your half-exact functor, you do not have to use a projective resolution or an injective resolution. Any acyclic resolution will do. Okay, so that's maybe, I think that's sometimes called the acyclic models theorem or something. But anyway, so so therefore that's kind of helpful because we embedded every it's easy to construct. It's much easier to construct like projective resolutions than it is to construct injective resolutions in many contexts, right? Every module, it's kind of obvious that every module is a quotient of a free module, and it's not obvious that every module can be injected into an ejective module. It was much more obvious that every G module could be injected into a co-induced module. We just proved that in like 3 lines. Okay, and so therefore, we can use, anyway, so I'm saying you can use, for your resolutions themselves, you can, instead of projective modules, you could use weakly projective modules, and instead of injective modules, you could use weakly injective modules. Okay. All right, so now I want to turn the page and start talking about how do you prove this Shapiro's lemma thing. And so the first thing that I want to do is I want to kind of restate Shapiro's lemma in a stronger and more directly module theoretic form. Okay, so if I have a subgroup of a group, M is going to be a G module, N is going to be an H module. So the homological version of Shapiro's lemma is going to be an equality of Tor functors. Not here I mean natural isomorphism. So Tor of so here to clarify here, so M is a G module. So when I say Tor as a ZH module, well, I mean, of course, that you restrict it to the underlying ZH module. Later, maybe in other places I might clarify that I'm restricting it, but here I'm trying not to clutter up the statement. And so the statement is that Tor over ZH from M into N is the same as Tor over ZG from M into the induced module. Okay, so in fact, all your Tors over the group ring ZH can be computed in terms of Tors over the group ring ZG. And then we have the cohomological Shapiro lemma, which is it's the same thing with X instead of Tor and with induction replaced with co-induction. Okay. And then we have this third thing, which I guess I'm calling bonus Shapiro. It is going to kind of fall naturally out of my approach to it. Later on, Harari will want this result anyway, so I'm not wasting our time. This is slightly more general, I guess, than Harari's proposition 1.39. So it's a different looking one for the X. Here I had a Tor and an ind. Here I had an X and a co-ind. You can also have an X and an int. Okay, and so you do notice that I switched M and N from parts A and B to part C. Okay. All right, so these are the three versions of Shapiro's lemma that I want to prove. And so what's going on? These definitely imply parts A and B are the Shapiro's lemma that I mentioned a couple of pages ago. So that's very easy to see because remember, group homology with coefficients in a module n is tor z into n. Okay, so if I take homological Shapiro and I take m to be equal to z, right? Then on the left-hand side, I'm getting the group homology of n, and on the right-hand side, I'm getting the group homology of n div n. Okay, so by nothing, you just plug in m equals z and use our interpretation of group homology in terms of Tor functors, and you immediately get this, and this is the homological thing that I called Shapiro's lemma before. Similarly, if you take part B and you apply m equals z, well, again, maybe even more importantly, then we know that our group homology is xed from z into the module. Okay, and so therefore we get, well, we just plug it in. And so we get that our nth group homology of n is equal to, with the H module n, its nth group homology is equal to the G group homology of the co-induction. Okay, so clearly parts A and B are enhanced versions of what I said before. But it sort of suggests that maybe the way to prove this is not really, maybe it doesn't have that much to do with group rings. Maybe it's more about modules over rings. Okay, and it is if you want to do it that way. So I have an approach to this. I don't know. There's not, I've seen every part of this approach elsewhere, but I'm not sure I've seen it kind of presented all together. So I want to give you three identities. They're all adjunction identities involving Hom and tensor regarding a change of rings. Okay, so I have a homomorphism of rings. I am not allowed to assume that these rings are commutative because, spoiler alert, in order to deduce what I want, the homomorphism of rings is going to be the homomorphism from the group ring of H into the group ring of G. Okay, so in my intended application, these rings, well, if G and H are non-commutative, then these rings are not going to be commutative. Okay, so I have these three identities. I'm not going to prove these identities. They're often left as exercises, so maybe I will leave them as exercises to you. But if you say, hey, I tried to prove this exercise, what gives? How do you prove it? We can talk about it. So the first one I'll call the Hom tensor identity. Okay. And so, all right, it kind of is what it is. You have an R mod. This one is maybe the most familiar. This one you may have seen like from my commutative algebra class in particular, in the case where the ring is commutative. So you have an R module M, you have an S module N, and oh, so now, by the way, I'm being heavy-handed. So here, what is this res SR? Well, N is an S module, but I really want, and so of course I can view it, if I have an S module and I have a homomorphism, I can pull back by that homomorphism and view it as an R module, and I've decided to be very heavy-handed. So just that very familiar pulling back your S module to be an R module, that is a functor, so I'm calling it res, okay? And so, but otherwise, except for this, you would probably write HOMR M into N, and there's kind of only one thing that could mean. So HOMR from M into my S module restricted to be an R module is equal, naturally isomorphic to HOMS of M tensor to S into N. Could you raise your hand if you've seen this identity before? So, okay, so some people, 2 people so far have raised their hands. And Menzalis, you've probably seen it. Okay. Anyway, so again, if you want to be a little bit fancy about it, and there are times where it's simpler to say the fancy words, I find this is saying that that the tensor and the restriction are adjoint functors to each other. What does that mean? It means exactly this. Okay, this natural isomorphism of functors. But when you have an adjoint pair of functors, Unfortunately, in my current state of brainwaves, it could be confusing. You want to keep track of which one's on the left and which one's on the right. Okay, and so this is the left adjoint, and this is the right adjoint. Okay, so tensor product is. I mean, again, you see this in commutative algebra. Maybe I didn't say, hey, they're adjoint functors, but I said, you know, you can if you can pull back an S module to an R module, and you can push forward an R module to an S module. And what did I mean by module push forward? I meant tensor product. Okay, so I was indicating that these two processes are well, they're adjoint. Okay, now I have a Hom identity. Okay, so this one I think is, I mean, I've definitely seen it. Obviously, how would I not have seen it before? That doesn't make any sense, but it's less common, I guess. So still M is an R module, S is an S module, and now we have a Hom from N viewed as an R module into M is the same as the Hom over S modules from N into Hom R SM. Okay. If you were, I guess one way to believe this is if you were working over fields, then then tensor and Hom, you know, Hom has a lot to do with like dual vector spaces. And so if you've never seen this before and you just want to kind of believe it, I would suggest that you do this in the case of vector spaces over a field. Okay. Okay. Yeah. Okay. And so what is this saying? This is saying that now it's interesting. So the restriction has, if you see that before, way back when, I was asking this question in a special case. I was saying, I have this restriction functor from ZG modules into ZH modules. Wouldn't it be nice to have something going in the other direction? Well, what I'm saying is not just for ZG and ZH, for any homomorphism of rings, you actually have two very reasonable things going in the other direction. There's two things that are adjoint to the forgetful functor from S modules to R modules. The left adjoint to the forgetful functor is the tensor product with S, and the right adjoint to the forgetful functor is the Hom with S. Okay, so that I think is beginning to, you know, we're kind of understanding where this induction and co-induction are coming from. Right. Let's see. Whoa. Where's the third identity? Oh no. Okay, so what's the third identity? So the third identity is really, hold on, let me just, I think I said it very well somewhere else. Give me a second. Yeah. So the third identity that I want here is I want a tensor identity. I had a tensor Hom followed by a Hom, and now I have a tensor identity. Okay. And it's this one, the non-commutativity of the ring and this level of generality, we do have to make some care. So M is a right S module. Okay, so in this level of generality, there's some left-right stuff going on. N is a right R module. Again, I have a ring map from R to S in all cases. Okay, that was the tricky part. And then so this is sometimes called the telescoping tensor identity, I think. So this one, maybe for commutative rings, will be familiar, or maybe in general will be familiar to some of you. So maybe I'll make it even more dramatic. Okay. So first, let's just check that this all makes sense, right? So N is a left R module. That's correct for doing this tensor product. S is an SR bimodule. Great. So I do the tensor product, the R stuff disappears, and what's left is a left S module. Great. Well, now you see that in general, I really do want M to be a right S module in order to do this tensor product stuff, right? As we talked about. Okay, so this, it kind of has to be this way. I'll explain why. Hopefully, I'll explain why. If we're actually working with group rings, then the left-right stuff is nothing to worry about. Okay, but someone, what's the answer? What is this canonically isomorphic to? Hint, I said telescoping tensor identity. So weird.
Is it the restriction of M to be an R module on
Okay,
tensor identity?
Yeah, which good. Yeah, for some reason, I don't know why I wrote it differently before. So okay, why not? Restriction from S to R of M, whichever after we're just going to write as M, tensored over R with that. Yeah. So telescoping meaning that kind of the S is canceled. Okay. Great. And so again, these are all exercises for you. Okay. I mean, you don't apply some crazy theorem. You literally write down, the map, but between them. Okay. So right. Now I want to come back to Earth, and I want to specialize these results to the case where our homomorphism is the homomorphism of group rings here, right? Okay, so in the first case, where I had the Hom tensor identity. Okay, I kind of have a lot. I turned the page, unfortunately, but there's kind of nothing to do if you just take that Hom tensor identity and you specialize here, then you're going to get this Hom, and then what you were supposed to get is you were supposed to get, like, what was this supposed to be in general? In general, this was supposed to be S tensored over R. Maybe it helps to see it again. Okay, so this is the identity here. Okay, and so yeah, so by nothing, just by applying that, you're going to get the tensor product, and lucky for us, we gave a name to that exact tensor product. Okay, and so that tells us that so if you apply the first, you apply the tensor Hom identity to the homomorphism of group rings, you get this. You get this natural isomorphism, and what does this tell you? This tells you that induction and restriction are an adjoint pair. Okay, that's useful. This is in very classical representation theory. You see something like this. There's something called like Frobenius reciprocity in classical representation theory, which is not as fancy as it sounds, and it's kind of a less categorical shadow of this adjunction between induction and restriction. Okay, but then you apply the second identity, the Hom identity. Let's remind us what it was. It was this. Maybe it's helpful, rather than to write it down, it's helpful to look at the general identity and see what happens. So if I take R to be ZH, then I get ZH, and if I take Hom over ZH from ZG into M, that is the co-induction. Okay. So you see that there's nothing going on here. I'm literally just applying this in a special case. And then that tells us that also co-induction is adjoint to restriction, but whereas induction was the left adjoint to restriction, co-induction is the right adjoint to restriction. So okay, there's a place for it, a functor can have both a left adjoint and a right adjoint, here it is. Okay, and then what about this third identity? Yeah, so there's a little bit of a discussion here. I guess I have to come back over here because, yeah, so let me come back over here and make a couple other comments, because I really did have like right module and then a left module, and that's not what's happening here. So I need to, yeah, I'm sorry. Unfortunately, I was so busy. I had kind of written up my notes like not so nicely, and then I was just recopying them like right before the class started, and I think I forgot forgot to copy this stuff. You can't see it, but it's right there. So in general, if I take a tensor product of modules and I want to kind of reverse the, if everything were commutative, then the tensor product is commutative, right? A tensor B is canonically isomorphic to B tensor A over a commutative ring. It doesn't make sense to do B tensor A over a non-commutative ring, unfortunately, because B needed to be a left R module, and A needed to be a right module. And by the way, this tensor product is just a Z module at the moment, right? And so the canonical isomorphism, again, though, as I think I mentioned before, if you want to switch from left modules over a non-commutative ring to right modules, you have to switch the ring. You have to switch the ring to the opposite ring where the multiplication is literally reversed, okay? So this is the fancier version of the canonical isomorphism with tensor products. And of course, over a commutative ring is naturally isomorphic to its opposite ring, and we don't have this fun conversation, okay? So this is what happens in the non-commutative case. But again, recall that ZG is canonically isomorphic to its opposite ring. The isomorphism is induced by G goes to G inverse on G. Right? Every group is isomorphic to its opposite group, and that induces a canonical isomorphism from the group ring to its opposite. And so what am I saying? What I'm saying is that we can move ZG modules from left to right, or the other way around, without any harm. Okay, so for this commutative ring, it doesn't matter. You see a right module, you make it a left module. Okay. All right, and so having said that, well, here's the telescoping tensor identity. So if M is a G module and N is an H module, same as it is in all three cases. And so I take, again, here I really did mean a res, right? So technically I mean a res down to ZH of M, but most people just write this. And then that's the same as if I took the tensor product over ZG with ZG tensor N. Okay. And then of course by definition, sorry, that's what's happening. My camera is, I was trying to understand why things were getting told. Okay, so yeah, and so this telescoping tensor identity, or this tensor identity in this case, is basically just saying that, well, this is what it's saying. It's saying that M tensored over ZH of N is canonically isomorphic to, naturally isomorphic to M tensor over ZG of N. Okay. So how are we doing here? Like this sounds good. It sounds useful, right? Where are we going though? If you take 3 and you look at it, I claim that this is the n equals 0 case of the homological Shapiro lemma. So the Shapiro lemma was something with tors over the group ring, right? But tor 0 is the tensor product. Okay, right? The homological is like Shapiro lemma should be, tor n of m comma n equals canonically isomorphic to tor n over zh of n comma n is canonically isomorphic to tor over zg n of m comma ind. And so this is the n equals 0 case of the homological Shapiro lemma. That's helpful. Okay. And then if you do two specialized to g, I claim that that's the n equals 0 case of the cohomological Shapiro lemma, right? So this one. And in a similar way, because the cohomological Shapiro lemma is with x, right? So it's xn over zh of mn is equal to xn over zg of m coind n, but the n equals 0 case of x is hom. Okay, so this is good. We're making, and again, there's several ways we could proceed. We could try to make a dimension shifting argument at this point. By the way, that would be something to try to do. So I want to make a really pretty simple ring theory / homological algebra. I think, yes, I think I'm not, did I? Yeah, no, I did. For instance, because I didn't have time to copy down the proof of this. So here's a theorem. I guess I'm not going to prove it. I probably won't even, we'll probably end it before I prove it anyway. I can talk about it next time. It's actually quite easy to prove, okay? So now here's the homological algebra fact that does everything for us. So 3 parts in analogy to the 3 parts that I have here and the 3 things I want to prove. So first of all, in the first part, I have a flat ring homomorphism. What does that mean? Well, I have a ring homomorphism. Any ring homomorphism makes S into a R module, left R module. And so I want S to be flat as a left R module. Maybe I should say, so the hypothesis is flat, flat, projective. Of course, we are going to apply this to the ring homomorphism from ZH to ZG. And as is an exercise in your homework, ZG is a free ZH module. So that's so much stronger than we need. So worry not, ZH to ZG is free, so it's flat, flat, and projective, not a problem. Okay. But this is just exactly what we need in order to make a very, very short argument go through. Okay, so if I have an R module M and if I have a right R module M and a left S module N, then there's some relation between the adjunction between the Hom and the tensor is propagating its way up to the torus is what's happening here. So there's 2 of these just to be, I want to make a careful balanced statement over a general non-commutative ring. The first one will be good enough for us. So anyway, you see that tor n of M over N over R is naturally isomorphic to tor over S when you extend scalars to S. So that certainly sounds like what we need in order to prove the homological Shapiro lemma. Okay, and then the second part is kind of as an analogous version. So we have a flat ring homomorphism. Now M and N are both left modules. M is a left R module, N is a left S module. And now for all N greater than or equal to 0, we have this natural isomorphism for the X group in terms of the tensor product. So this one to me, in fact, this one has got to give us homological Shapiro. You look at this one looks like bonus Shapiro because it involves the X, but on the other hand, it involves a tensor product, right? And then we have the part C. So for part C, okay, maybe this projective homomorphism, I don't hear that all the time, but it's a ring homomorphism where S is projective as an R module. Okay, M is an S module, N is an R module, both on the left. And then we get the natural isomorphism between the X groups over R and the X groups over S, where you replace N with this thing that's going to be the co-induction. Okay, so that's a theorem. I think probably in the following lecture, I will prove part A for you, and just so you can see how easy it is. I mean, it really is, it's just a few lines. I guess why flat? Well, if something is flat and you have an exact sequence, like a resolution, and you tensor with the flat thing, it's still exact. That's like a third of the proof right there. So I'm going to start with the projective resolution of something, which is what I'm supposed to use to compute tor. And if I tensor with something flat, I'm still going to have a resolution. It's still going to be exact. And whenever you base change a projective module, it'll still be projective. So because the ring homomorphism is flat, if I start with the projective resolution of anything over R and I tensor it to S, then I'm going to get a projective resolution in the category of S modules. That's like half of the proof right there. Okay. And so you see that if you apply part A to this group homomorphism, and now I think you'll find unfortunately, that that I mixed up my m and my n in order to apply this directly. So I think here in the setup, m is an R module, and so and n is an S module. So if I take R to be ZH, then now m is a ZH module and n is a ZG module. I mean, there's nothing terribly wrong with that. It just happens not to be the way I set it up. The way I set it up was that m was the ZG module and n was the ZH module. So sorry, you just switch. Literally, you go back to you go back to this statement, and you should have interchanged the names m and n here. Okay. So if you apply part A of this sort of easy homological algebra fact, then so you get this result. Maybe we should just check it. So if R is ZH and S is ZG, then we're saying that Tor over ZH of m into n is Tor over ZG of ind of m into n, and that is keeping in mind that Tor is commutative. That is the statement that we want. Again, there's a probably yeah. So again, except for the fact that I that I mixed up my m and my n, it's okay. But again, you can switch the Tors around. I did the n equals 0 case. You can switch the Tors. You should switch the ring to its opposite, but that's okay. Or maybe anyway, yeah. Or maybe you should use the second equality in this case. Okay, maybe that's a better way to do it. Yeah, that sounds right. Anyway, whatever. You can have it either way. So if you and so then in part C, if I take R equals ZH and S equals ZG, again, this ZG is a free ZH module, so it's definitely projective. And then, what am I getting? Again, here I should literally switch the roles of and whatever. I can have it where I changed what I was calling it. And so here I get that the ZHX of m into n is the ZGX of m into the co-induced module, which again, accepting only that I unfortunately switched what I said about m and n is what I have here. Okay. Just stop and think about that for a second. Actually, maybe it's not switched here. Maybe it's okay here. Whatever, it's fine. Yeah, it doesn't look like it was switched. Yeah, here it's correct. Yeah, so here notice from the first two parts to the second part, I flipped something around as well. So part C is literally correct. Okay. Okay. And so yeah, and then if you apply part B, and again, I think you need to. Okay, so I'm just repeating myself. Okay, so this is a very, very, very detailed sketch of the proof of homological Shapiro, cohomological Shapiro, bonus Shapiro, all three of which we're going to need and use later. Again, I'll come back. I'll prove. I will next time. I will prove. If I were in a different mood, I would just do it now, but I guess I'm not. Next time I'll come back and I'll prove part A. It really is like 3 lines, and then we're good. I think we're finally. I'm not really doing things again. I really hope that as soon as things sort of get underway, that I will be happy to follow Harari very closely. I still think I will. At the moment, there's just anyway. So I'm definitely doing stuff that he's doing in chapter 1, and the extra homology stuff that I'm doing is stuff that he's going to do later on anyway. So I'm not, everything that I'm doing is actually very close to what's in Harari, and yeah. Anyway, I think we're not too far from being finished with chapter 1 of Harari. That's where we're going. All right, well, see you later this afternoon if you like, and if not, see you on Friday for the problem session. So.